The film begins in silence, a silence so vast it seems to swallow even thought itself. Across this quiet expanse, stars hang like scattered embers, galaxies drift like frozen waves upon a dark cosmic ocean. Beneath it all lies something unseen, something more fundamental than matter, more enduring than light. The fabric of Spacetime. It is the hidden geometry of existence, the stage upon which reality itself performs. It bends when planets move, it trembles when stars collapse, it stretches as the universe expands, and yet, for all its grandeur, it may not be indestructible. What if this fabric could tear? What if the smooth continuum of reality fractured like shattered glass? What if the very stitching of existence came undone? A seam splitting in the invisible skin of the cosmos. A rift opening where time no longer flows, where space no longer holds, where causality itself dissolves into silence. We glimpse its possibility. In the darkest of places, in black holes shredding stars into ribbons of fire, in gravitational waves that ripple like hammers striking a drum, in the restless foam of quantum fields at the smallest scales. Each phenomenon is a whisper, an omen, a reminder that the stage of reality may not be permanent. The question rises, haunting and inescapable. What happens if space-time itself is torn apart? Would matter collapse into nothingness? Would time unravel? Would the laws of physics end? Or would the rupture reveal something deeper, stranger, hidden truth behind the veil of existence? This is not only science, it is a meditation on fragility, on impermanence, on the terrifying possibility that the universe itself may not endure. The story of tearing space-time apart begins not with rupture, but with revelation. For most of human history, the universe was imagined as a static doomer, fixed architecture of stars pinned to an eternal canvas. Space was infinite, time was absolute, and the stage of existence was thought to be unchanging, untouchable. This certainty began to fracture in the early 20th century. In 1905, Albert Einstein introduced special relativity, a theory that fused space and time into a single fabric of events. 10 years later, in 1915, his general theory of relativity expanded that vision into something stranger still. Gravity was not a force in the Newtonian sense, but the bending of space-time itself. The insight was staggering. What had once been considered empty nothingness was revealed as an active player, a geometry capable of shaping motion and defining destiny. Stars bent the paths of planets, black holes warped light itself, and the entire cosmos became a living map of curvature. But even before Einstein, the seed of this realization had been planted. In 1908, Hermann Minkowski, Einstein's former mathematics professor, proclaimed that space and time should not be thought of separately, but as inseparably fused together in a four-dimensional continuum. What we experience as the ticking of seconds and the distance of miles were, in truth, threads of a single woven fabric. The first proofs soon followed. In 1919, during a solar eclipse, Arthur Eddington and his team observed starlight bending around the sun exactly as Einstein's equations predicted. The newspapers declared, "Einstein triumphs." The invisible fabric of space-time had been glimpsed through its warping, but woven into Einstein's equations was something unsettling. His solutions did not merely allow for smooth, gentle curves of geometry, they also predicted extremes, places where space-time could fold in on itself, where curvature could grow without limit. In 1916, Karl Schwarzschild, serving on the Eastern Front during the First World War, wrote down the first exact solution to Einstein's field equations. It described a point of infinite density, surrounded by a horizon beyond which no light could escape. A singularity at the time, this was treated more as mathematical curiosity than physical reality. Even Einstein resisted. He believed nature would not permit such catastrophic collapse. The universe, he thought, must conspire to keep itself smooth, unbroken, but nature had already begun to whisper otherwise. In the decades that followed, astronomers discovered stars whose behaviors hinted at the fabric's limits. In the 1930s, the strange orbits of companion stars suggested invisible partners objects, so dense their gravity defied comprehension. By the 1960s, the discoveries of pulsars and quasars forced a reckoning. Pulsars rapidly spinning neutron stars were evidence of matter compressed nearly to the breaking point. Quasars, blazing with the energy of entire galaxies, were powered by something even more extreme, the feeding of black holes. Spacetime was no longer a placid stage. It trembled, collapsed, and roared. And then came 2015, a century after Einstein's prediction. The Laser Interferometer Gravitational Wave Observatory LIGORA recorded the faintest tremor in existence. Two black holes, billions of light-years away, had collided, sending ripples through space-time itself. Not through matter, not through air, but through the fabric of reality. Like a drum struck with unimaginable force, space-time rang. The detection was history's first direct evidence that space-time could move, stretch, and quake. It was not unbreakable, it was elastic. And if elastic, then perhaps fragile. Each of these discoveries built upon the last, forming a picture that was both awe-inspiring and disturbing. Einstein's relativity had revealed a dynamic fabric. Schwarzschild had uncovered its singular collapse. Pulsars and quasars showed it manifest in the night sky. LIGO revealed its tremors. Step by step, science was uncovering a cosmos where the fabric of existence could bend, twist, and perhaps, under the right conditions, tear. But the question lingered. What does it mean for reality itself to rupture? If space-time is the very stage upon which time flows and matter moves, what lies beyond the edge of the stage? If the stitching of the universe comes undone, what replaces it? The discovery phase of this story is not merely a chronicle of equations and instruments. It is the dawning realization that the cosmos is not eternal stone, but living cloth-woven, trembling, and vulnerable. The ancients had imagined the heavens as crystalline spheres, immutable and eternal. The modern age revealed something far stranger, a geometry alive with tension, stretching toward collapse, whispering of rifts we cannot yet fathom, from the eclipse of 1919 to the gravitational waves of 2015. A single truth has grown clearer with time. Space-time is not empty, not invincible, and not immune to rupture. The very stage of reality may carry within it the seeds of its undoing. For centuries, space had been imagined as an empty void, an infinite stage that simply was, incapable of rupture or decay. Even Einstein, whose equations hinted at collapse, recoiled at the idea that space-time itself might break. He once dismissed the singularity as nothing more than a pathological feature of mathematics, a trick of equations with no counterpart in reality. To imagine the fabric of the cosmos tearing apart seemed too extreme, too unnatural, and yet nature was relentless. In its defiance, the shock began with singularities, the mathematical inevitabilities lurking within general relativity. In the 1960s, Roger Penrose and Stephen Hawking proved with a series of rigorous theorems, that singularities were not rare quirks, they were inevitable outcomes of gravitational collapse. If a massive star burned through its nuclear fuel and gravity gained the upper hand, its core would collapse not into some exotic particle configuration, but into a region where space-time curvature grew infinite. At such a point, the equations of physics themselves lost meaning. It was not simply matter that collapsed. It was the very geometry of the universe. The idea was staggering. If singularities were real, then the fabric of reality contained Ige's boundaries, where space and time ceased to function. Relativity, the most elegant description of the cosmos ever written, carried within it the seeds of its own destruction. For the scientific community, this was a revelation both profound and unsettling. Physics had long been built on the belief in continuity. Equations could be extended, fields could be smoothed, predictions could be made. But singularities broke that trust. They marked places where time ended, where predictability dissolved, where the continuity of nature collapsed into unknowable silence. The event horizon, introduced through Schwarzschild's solution, deepened. The unease. It was the invisible boundary around a black hole beyond which no signal, no particle, no ray of light could escape. To an outside observer, anything crossing this threshold seemed to vanish forever, swallowed not into another region of space, but into non-existence. The horizon was not a wall of matter. It was geometry itself, sealing shut. To Einstein, this was deeply uncomfortable. He resisted the idea that black holes could exist as physical entities. He proposed counter-arguments, hoping nature would find a way around singularities, but the mathematics would not bend. And then, as telescopes probed deeper into the skies, reality confirmed what the equations had whispered. These storms of geometry were not only real, they were common. By the late 20th century, evidence was mounting that nearly every galaxy, including our own, harbored a supermassive black hole at its core. These were not rare anomalies. They were the anchors of cosmic structure. The tear in space-time was not a distant possibility. It was the foundation of the universe's architecture. The shock only deepened with the discovery that the universe itself had a singularity in its past. The Big Bang, the cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson, revealed fossil light from an early universe that had once been hot, dense, and compressed into a point of unimaginable energy. The universe itself had begun from a rupture in space-time. The realization was profound. Singularities were not exotic outliers hidden in stellar corpses. They defined both the beginning of time and the fate of stars. Reality, it seemed, was bookended by rupture. Yet, the most jarring revelation came at the end of the 20th century. Astronomers, measuring distant type Ia supernova as standard candles, expected to find that cosmic expansion was slowing under gravity's pull. Instead, they found the opposite. The universe's expansion was accelerating. Something, unknown later, named dark energy was stretching space-time faster and faster. This was more than surprise. It was disorientation. Gravity, the great binder of matter and energy, was not supreme. Instead, an unseen force was tearing galaxies apart, pushing the fabric of space-time toward an uncertain fate. No longer did the universe's geometry simply bend, it was being pulled, stretched, and destabilized. If this acceleration continued unchecked, the cosmos might one day rip itself apart in a cataclysm known as the Big Rip. The shock was twofold. Not only could spacetime collapse into it could also unravel under expansion. It was fragile from both extremes, crushed to a point or stretched to oblivion. Einstein had once called the cosmological constant his greatest blunder, but with the discovery of dark energy, it returned with haunting significance. His equations had allowed for it all along. He had glimpsed the possibility that geometry itself could be unstable, but dismissed it. Now the universe forced physicists to confront it. The implications rippled outward into philosophy. If spacetime could end, what of causality, memory, meaning? If time itself could rupture, then everything past, present, and future was contingent upon a fabric that might not endure. The stage of existence was not eternal, it could fail. Stephen Hawking captured the unease with his work on black holes. His famous prediction of Hawking radiation suggested that black holes evaporate, slowly leaking energy back into the cosmos. But this raised a paradox. If information fell into a black hole and the black hole evaporated, what happened to the information? Was it lost forever? If so, the laws of quantum mechanics, laws that demanded information be preserved, would be broken. This was not just a battle of equations. It was a war over the very coherence of reality. If information could be destroyed, then the universe itself might not be logical. Spacetime's tear would not simply erase matter. It would erase the rules of existence. In the shock of these discoveries, physics entered a new era of humility. The cosmos was not a smooth, eternal machine. It was a fragile geometry, a vulnerable stage, haunted by collapse and dissolution. The very fabric that seemed to grant stability was revealed as conditional, unstable, prone to rupture. And so the central terror of cosmology emerged. If spacetime can break, then reality itself is not absolute. What we take as permanent, the flow of time, the order of cause and effect, the vast distances of galaxies, may all be contingent on a fragile geometry destined to fail. The scientific shock was not only in the mathematics, nor only in the telescopic confirmations. It was in the dawning recognition that physics itself might be incomplete. Relativity and quantum theory, the twin pillars of modern science, both pointed towards spacetime tearing apart, and both contradicted each other at the brink. Somewhere, at the edge of a singularity or at the onset of cosmic acceleration, lies a realm where both theories fail, where equations collapse into silence. That silence is the sound of rupture, the sound of reality itself undone. The shock, once unthinkable, had become inescapable. Spacetime is not invulnerable. It can bend, it can stretch, it can collapse, and under the right conditions, it can break. The shock of rupture had unsettled physics, but shock alone could not be the end. If spacetime could truly tear, then science had to investigate its edges, its fractures, its hidden seams. What followed was a century of inquiry and immense effort, to probe not only stars and galaxies, but the very geometry in which they reside. The first step was to measure expansion with greater precision. Type Ia supernova, the brilliant explosions of dying white dwarfs, became standard candle celestial rulers of distance. In the 1990s, teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees used them to map the cosmos acceleration. Their results were startling enough to win the Nobel Prize. The universe was not only expanding, but accelerating into an unknown future. Space-time itself was stretching, and the rate of that stretching was increasing. To understand geometry on its grandest scale, cosmologists turned to the cosmic microwave background. Satellites such as WMAP and later Planck mapped the faint glow. left from 380,000 years after the Big Bang. The delicate ripples in that fossil light carried the imprint of cosmic curvature. Was the universe shaped like a sphere, a saddle, or a flat plane? To the surprise of many, the data showed near-perfect flatness. The geometry of space-time was balanced with uncanny precision, as though stretched taut on the thinnest line between collapse and endless expansion. But flatness did not mean safety. If anything, it raised new anxieties. A flat universe, combined with dark energy, suggested acceleration without bound. Galaxies receded faster than light, not because they moved through space, but because space-time itself carried them away. The cosmic horizon grew. More of the universe slipped beyond visibility, beyond reach. Every year, hundreds of galaxies crossed that horizon, disappearing forever into darkness. Geometry itself was hiding them. Astronomers probed the fabric in new ways. Baryon, acoustic oscillations, fossil sound waves imprinted on galaxy distributions, offered another ruler to measure expansion. These patterns, traced by vast surveys such as the Sloan Digital Sky Survey, revealed how space-time stretched across billions of light. Again, the data whispered of acceleration, of a fabric not stable but restless. Yet investigation did not end at cosmic scales. Telescopes also probed local laboratories of rupture black holes. Around these dark giants, matter spiraled inward at near-light speeds, forming glowing accretion disks that radiated in X-rays. Observatories like Chandra and XMM Newton traced these emissions, mapping the gravitational violence at the brink of collapse. It was as though astronomers stood at the edge of a cosmic seam, watching reality bend toward fracture. The discovery of gravitational waves in 2015 offered another tool. LIGO and Virgo detected ripples in space-time itself, born from colliding black holes. These were not metaphorical tremors. They were literal oscillations of geometry, stretching Earth by fractions of a proton's width. Each detection confirmed that space-time was not rigid but elastic, capable of vibrating, ringing like a drum when struck by cataclysm. And with each ring, physicists saw not only resilience but fragility, the possibility that too great a strain might one day rip the fabric. Deeper still, quantum physics unsettled the vision of space-time as smooth. At the Planck scale, 1035 meters, geometry was thought to dissolve into foam, a froth of uncertainty where distances and durations lost meaning. Virtual particles flickered in and out of existence, warping space-time with microscopic tremors. Physicists like John Wheeler described this realm as quantum foam, a seething instability beneath the apparent smoothness of reality. If space-time could foam, could it also fracture? Could microscopic tears grow, propagating outward, destabilizing the cosmos itself? The search for such signs extended into particle accelerators. At CERN's Large Hadron Collider, collisions at trillions of electron volts tested whether the Higgs field, the field that gives particles mass, was stable. The measurements suggested our universe might not sit in a true vacuum but in a metastable state, a delicate plateau that could one day collapse into a lower energy configuration. If triggered, this vacuum decay would not merely rearrange particles, it would rewrite space-time itself, tearing the fabric and replacing it with alien laws of physics. Astronomers also searched for scars on cosmic scales. The cosmic microwave background was combed for anomalies, sun-explained cold spots, asymmetries, or bruises that might hint at collisions with other regions of space-time. Some researchers speculated these features could be signs of a multiverse, where universes occasionally collide, tearing and distorting the fabric at their boundaries. The evidence remained inconclusive, but the possibility lingered like a haunting shadow. Perhaps space-time had already torn, long before humans were here to notice. Closer to home, meteors offered another line of inquiry. In 2014, a meteor known as Siena's, the 8th of January 2014, struck Earth's atmosphere at anomalous velocity so fast it seemed to come from interstellar space. Some suggested it might even bear materials alien to our universe's chemistry, fragments from beyond known physics. Expeditions were launched to the ocean floor to recover its remains, to test whether matter itself could carry the fingerprints of ruptured space-time. The investigation expanded beyond astronomy into computation. Supercomputer simulations modeled billions of years of cosmic evolution, tracing how dark matter scaffolds formed galaxies, how dark energy stretched them apart, and how black holes tore their centers. These digital universes were laboratories of rupture, showing in slow motion how geometry might evolve, collapse, or unravel. Yet each simulation revealed the same paradox: stability at one scale, fragility at another. Stars formed while galaxies faded. Galaxies thrived while cosmic horizons grew. Local order against global dissolution. The deeper the investigation went, the clearer it became that space-time was neither invincible nor uniform. It was layered in fragility. At stellar scales, collapse led to black holes. At cosmic scales, acceleration led to horizons. At quantum scales, foam threatened instability. Everywhere, geometry was tested and, everywhere, cracks seemed possible. Philosophically, this marked a shift. Reality could no longer be taken as a smooth continuum. Instead, it appeared contingent, provisional, perhaps emergent from something deeper. If space-time was woven, what were its threads? If it could tear, what lay beneath the tear? The search for answers only multiplied the mystery. Every telescope, every detector, every simulation pointed to one conclusion: space-time is not eternal. Architecture, but living geometry, capable of trembling, collapsing, stretching, perhaps even breaking. The smooth stage of existence was not a guarantee. It was a question. And so, the deeper investigation did not calm the shock. It intensified it. Each discovery widened the sense that the cosmos we know rests on fragile ground, on a geometry that could one day unravel. The question was no longer whether space-time could tear. The question was, when, where, and what lies beyond the tear. The deeper science peered, the darker the mystery became. Space-time, once imagined as a serene stage, revealed itself as unstable, haunted by possibilities of rupture. The calm continuum of Einstein's equations had transformed into a battlefield of paradoxes, of contradictions that refused resolution. Every discovery only deepened the dread. Space-time was not safe. Black holes became the central icons of this terror. At their heart lay singularities, points where density soared to infinity, where geometry itself collapsed into nothingness. General relativity insisted such places existed, but it could not describe them. Equations diverged, logic faltered, and physics ended at the singularity. The event horizon, the black hole's invisible veil, was a mercy. It concealed the tear, hiding the incomprehensible heart from the outside universe. Yet this concealment raised its own paradoxes. The most troubling was information. When matter fell into a black hole, where did its data go? Quantum theory demands. That information is never destroyed, yet relativity allowed black holes to swallow it without return. If information truly vanished, then spacetime itself shredded logic, erasing the very rules of quantum mechanics. This was not merely a tear in geometry, it was a tear in reality's consistency. Hawking's theory of black hole evaporation sharpened the paradox. According to his calculations, quantum effects at the event horizon caused black holes to radiate, faint particles slowly evaporating over eons. But if a black hole dissolved into nothing while erasing the information it once contained, then physics lost coherence. The very laws meant to explain the universe contradicted one another. The storm at the horizon was not only gravitational, it was conceptual, a tempest in the foundations of knowledge. Beyond black holes, the universe itself carried signs of rupture. Cosmic inflation, an explosive expansion in the universe's first fraction of a second hinted that spacetime had once torn itself apart and rebuilt at unimaginable speeds. The inflationary field stretched quantum fluctuations into the seeds of galaxies. But the mechanism that drove it remains mysterious. Did inflation stop everywhere at once, or does it still continue in other regions, spawning bubble universes beyond our reach? If so, then our cosmos is but one patch in a quilt of ruptured spacetimes, a survivor of a far greater tearing dot. Another fear arose from the concept of false vacuum decay. If the Higgs field that underlies particle masses is metastable, then spacetime sits on a false floor. A random fluctuation or high-energy event could trigger collapse into a lower energy state. The transition would spread outward at light speed, a bubble of new physics rewriting particles, forces, and geometry. Within that expanding wall, atoms would disintegrate, time itself would break. The fabric would be torn not locally, but globally, erasing everything we know. Cosmologists also imagined the Big Rip, a scenario born from dark energy's acceleration. If the mysterious force stretching the universe grows stronger with time, expansion will not slow it, will accelerate into catastrophe. First, galaxies will drift apart, then stars will lose their orbits. Later, planets will be ripped from suns. At the extreme, atoms themselves will be torn, spacetime shredded into nothing. This is not collapse into a singularity, but dismemberment, into void existence pulled apart until nothing remains coherent. Evidence of fragility, also echoed through gravitational waves. The collisions of black holes revealed spacetime ringing, shuddering under strain. These were triumphs of detection, yet also warnings. Spacetime is not immune to violence. It trembles, it flexes, it resonates with catastrophe. If the universe is littered with such collisions, then spacetime itself is continually battered, a fabric surviving strain after strain. The question hangs heavy. What happens if one day the strain is too great? On the largest scale, acceleration cast the darkest shadow. Galaxies receding beyond the cosmic horizon are not destroyed, but for us they are erased. Their light can never reach us. Every second, more of the universe slips beyond recovery. In the deep future, only our local group will remain visible. All else will vanish. Spacetime itself enforces this isolation, stitching horizons that divide reality into unreachable domains. For humanity, the death of the sky is not theoretical. It is already underway. Philosophically, the escalation was unbearable. If tears, then causality itself may break. Past and future may lose coherence. Wormholes solutions to Einstein's equations that fold spacetime into shortcuts Salford, not salvation but paradox. They could permit time travel, closed loops, where cause follows effect in impossible circles. If wormholes exist, they are tears not only in space, but in logic. Reality would no longer be linear, but fractured, recursive, unstable, at each frontier. Scientists asked not only whether space-time could tear, but what such a tear would mean. Was it annihilation or revelation? Would a rupture destroy physics or reveal a deeper substrate beneath? Some theorists suggested space-time itself is emergent, not fundamental. Like waves on water, it may arise from something deeper: quantum entanglement, information networks, or unknown fields. If so, then a tear might not be the end, but a glimpse beneath the surface, into the true machinery of existence. Still, the dread grew. Everywhere physics looked, it saw fragility. Singularities concealed but undeniable. Inflation hinting at ruptures in cosmic birth. False vacuum, decay threatening annihilation. Dark energy promising dismemberment. Wormholes tempting paradox. Information loss mocking consistency. Gravitational waves testifying to strain. The very sky dissolving into horizon. The escalation of mystery did not comfort. It reminded humanity that its universe is not fortress but fabric, not immutable but vulnerable. Every star, every atom, every breath rests on a stage that may one day split beneath it. The haunting idea now pressed forward: space-time may not be stable. It may be temporary, contingent, destined to rupture. And when it does, no boundary of scale will protect us, not the stars, not the atoms, not even the laws of time. As the mysteries mounted, science was forced to enter the realm of speculation. Observations had carried cosmology to the brink of comprehension. But beyond that brink lay only conjecture equations pushed past their tested limits, dreams of physicists drawn across chalkboards, simulations of worlds never seen. To ask what happens when space-time tears is to step into this twilight, where theory becomes prophecy, where speculation tries to catch the echo of truth. The first pillar remained Einstein's general relativity, a triumph of geometry. Relativity revealed how matter and energy bend space-time, shaping orbits, guiding light, sculpting galaxies. Yet its singularity, theorems developed by Roger Penrose and Stephen Hawking, declared that collapse is inevitable under extreme density. Curvature diverges, creating singularities where the fabric of space-time ends. The theorems were merciless. They did not say singularities might exist, but that they must. To many, this was the ultimate proof that space-time cannot be whole. Somewhere, deep within black holes, or at the birth of the cosmos, it must tear. But relativity is only half the story. Quantum mechanics, the language of the microscopic, refuses to fit neatly into relativity's smooth curves. Quantum fields buzz with energy. Particles appear and vanish. Probabilities reign. At the Planck scale, y minus 35 meters, quantum uncertainty overwhelms geometry, shredding the concept of smooth spacetime into froth. If relativity predicts tears in collapse, quantum theory predicts tears in continuity itself. Reconciling them has become the greatest problem in physics and the source of the boldest speculations. One path is quantum gravity. In string theory, the universe is woven not of points but of vibrating strings, each frequency a particle. Extra dimensions beyond the familiar furl invisibly, and in this landscape, space-time itself is an emergent fabric. Collisions of brains' higher dimensional membranes could create entire universes, tearing and sewing space-time in ways unimaginable. Some theorists suggest our universe began as such a tear, a collision that released the energy of creation. If brains can collide, they can also rupture. A tear in spacetime could be not merely destruction, but the birth of another cosmos. Loop quantum gravity takes a different route. It suggests spacetime is not continuous at all, but built from discrete loops, finite quanta of area and volume. At the smallest scales, geometry is pixelated. A black hole's singularity in this model is avoided. Collapse halts when quantum loops resist further compression. Instead of an endless tear, there may be a bounce. A black hole could implode into a new universe, its rupture transformed into a passage. Our cosmos may itself be the rebirth of another, its geometry recycled through quantum resistance. Other ideas peer into the paradox of information. The holographic principle, inspired by black hole physics, suggests that spacetime itself is not fundamental but projected. Information may live not within volume, but on surfaces, encoded like a cosmic hologram. If this is true, then a tear in spacetime is less catastrophic than it seems. The fabric may rip, but the information persists on a boundary. Destruction may only be appearance. Beneath geometry, reality may remain whole, yet other speculations are darker. The stability of spacetime may depend on the Higgs field, which grants mass to particles. If this field is metastabilized, measurements hint then our universe floats on false vacuum. A quantum fluctuation could tunnel into a lower energy state, igniting vacuum decay. The bubble of true vacuum would expand at light speed, rewriting constants, annihilating matter. Spacetime itself would be torn and rewritten in an instant. Some physicists believe this may have already happened elsewhere, bubbles forming unseen beyond our horizon. The only mercy is speed. If it begins, we will never feel it. The multiverse extends speculation further still. If inflation never ended everywhere, then infinite bubble universes may expand forever, each with its own spacetime. Collisions between them could scar the cosmic microwave background, leaving subtle bruises of contact. Some cosmologists whisper that such marks have already been glimpsed, though the evidence remains contested. If universes can collide, then spacetime is porous. Tears may not be rare, but ordinary, stitched across boundaries beyond observation. Our cosmos could be one fragment adrift in an eternal sea of ruptures. Even time itself is not immune. Closed. Time-like curves, solutions to relativity's equations, permit loops in causality. In theory, tears in spacetime could fold time into circles, allowing events to influence their own origins. Yet this invites paradox, grandfather dilemmas, contradictions, logic undone. Hawking proposed the chronology protection conjecture, an idea that the universe prevents such violations. But this too is speculation, a guess at cosmic censorship. If time can loop, then spacetime is not only fragile but incoherent, a fabric that contradicts itself when stressed. Some theories turn to entropy. The second law of thermodynamics insists disorder always grows. Heat death, the slow fade into equilibrium, is geometry stretched thin, energy dissipated into silence. Here spacetime does not tear suddenly but erodes, unraveling across trillions of years. Others imagine the opposite, the big crunch, where geometry reverses, collapsing into fire. Still others fear the big rip, dark energy accelerating until atoms shred. Each fate is geometry undone, slowly, violently, or fatally stretched. Speculation also entertains extremes. Wormholes may connect distant points, shortcuts through folded spacetime. Yet to remain open, they require exotic matter-negative energy that defies known physics. If they exist, they are natural tears, doorways punched through geometry. Perhaps they collapse, perhaps they endure, perhaps they connect not only regions of space but separate universes. If so, then tearing spacetime could be not annihilation but travel, a cosmic migration through wounds in the fabric. Still, the greatest speculation remains humility. Perhaps spacetime itself is not real in the way we imagine. It may be a convenient illusion, an emergent structure born from deeper relationships of information. Some physicists compare it to temperature, not fundamental but collective, arising from microscopic motion. If spacetime is emergent, then its tearing may not be destruction but transformation. What appears as rupture may reveal the deeper architecture beneath the scaffolding of existence itself. In the twilight between science and imagination, these theories coexist uneasily. Some suggest safety, that tears are illusory, that information persists, that bounces replace singularities. Others predict doom, vacuum decay, rips, collapses, annihilations beyond resistance. Between them lies uncertainty, the acknowledgement that humanity stands not on bedrock but on fabric, fragile and strained. Each speculation extends the same haunting question: what happens if spacetime tears? Does the universe end, or does something else begin? The answers remain shadows, sketches on blackboards, equations whispering of truths beyond reach. But together they remind us of one thing: that spacetime, the stage of existence, is not eternal. Stone, it is cloth, woven, stretched, perhaps destined to split. And when it does, whether it brings revelation or ruin, it will reveal the deeper secret of reality. Speculation alone cannot hold the weight of the cosmos. Science, to move forward, must build instrument size that see the invisible, ears that hear the inaudible, machines that touch the untouchable. To ask whether spacetime can tear apart is to confront the limits of both theory and technology. Yet across the last century, humanity has constructed tools that reach astonishingly close to that fragile frontier. They measure trembling fabric, collapsing horizons, and the faintest scars of ancient ruptures. They do not answer the ultimate question yet, but they bring us nearer, pulling at the edges of the unknown. The most direct instruments are gravitational wave detectors. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO recorded the spacetime tremor from two colliding black holes. The signal was almost imperceptible, a ripple stretching and contracting space by less than the width of a proton. Yet it was real proof that spacetime is not static geometry but dynamic fabric, capable of ringing like a struck drum, each detection. Since through LIGO, Virgo in Italy, and Kagra in Japan has expanded the catalogue of cosmic ruptures, black hole mergers, neutron star collisions, even possible black hole neutron star unions. Each is a glimpse of spacetime shuddering at its breaking point. These detectors are crude prototypes compared to what may come, yet already they have rewritten cosmology. They prove that spacetime is elastic, not eternal stone, and that its stress lines can be heard across the universe. To probe the brink of rupture, astronomers have turned telescopes, not to visible light, but to shadows. The Event Horizon Telescope, a planet-wide array of radio observatories, captured the silhouette of a black hole in 2019. The supermassive monster in M87, The dark circle ringed by fire was not the hole itself, but the shadow cast by collapse. It was the first human glimpse of a horizon, the very boundary where space-time folds into itself. In 2022, the same technique revealed Sagittarius A*, the black hole at the heart of the Milky Way. These images are more than photographs. They are direct evidence that space-time can be pushed to the edge of rupture, to the threshold where geometry ceases to return signals. Every future refinement will sharpen our view of this brink, allowing us to see whether horizons themselves flicker, shimmer, or ripple under quantum strain. Beyond shadows lies light stretched to its limits. The James Webb Space Telescope, launched in 2021, peers across cosmic time, to when galaxies were young and geometry newly formed. Its infrared eyes see light redshifted by expansion, tracing the growth of structure across 13 billion years. Webb cannot see a tear directly, but it can see the fingerprints. Patterns in galaxy clustering, distortions in gravitational lensing, and anomalies in the cosmic dawn may all betray weaknesses in the fabric. In this way, Webb extends humanity's reach not to a single collapse, but to the global shape of space-time, testing whether its geometry bends toward stability or fracture. Dedicated missions will push further. The European Space Agency's Euclid telescope, launched in 2023, maps billions of galaxies to chart dark energy's role in expansion. The Nancy Grace Roman Space Telescope, set to follow later this decade, will survey wide fields with exquisite precision, searching for signatures of accelerated tearing. These are not casual experiments. They are designed explicitly to measure the fate of geometry. Their goal is to determine whether expansion will fade, stabilize, or run wild into a rip. Each dataset adds a pixel to the picture of cosmic destiny, but not all tools gaze outward. Some aim inward, to the quantum fields beneath spacetime. Particle accelerators, like the Large Hadron Collider, smash protons together at near-light speeds, probing the Higgs field and its stability. If the Higgs sits in a false vacuum, then spacetime is metastable, doomed to collapse into a state. Already, experiments hint that our universe may not be perfectly safe. Physicists search for clues in decay rates, scattering patterns, and subtle anomalies. Each collision is a test of whether spacetime is whole or precarious, a fabric stretched too tightly across unstable foundations. Future instruments grow even more ambitious. LISA, the Laser Interferometer Space Antenna, will fly in the 2030s. 3 spacecraft, separated by millions of kilometers, forming a gravitational wave observatory in orbit. Unlike LIGO, it will detect longer ripples mergers of supermassive black holes, the rumble of galactic-scale collapses, perhaps even echoes from the Big Bang itself. If inflation tore spacetime in its first instant, LISA may hear its fossilized roar. Other proposed detectors, like pulsar timing arrays, already hint at a cosmic background of gravitational waves, a low hum from the universe's earliest tremors. If confirmed, this background would be a record of rupture written across spacetime itself. X-ray telescopes, such as Chandra and the upcoming Athena mission, add another layer. They see accretion disks at their hottest, where matter spirals into black holes and spacetime nears the threshold of collapse. Their spectra reveal relativistic distortions, broadening and skewing as light struggles to escape curved geometry. Each measurement is a stress test of relativity, a probe of whether the equations hold under crushing densities. Deviations could signal the limits of smooth spacetime, the first cracks in the foundation. Computational tools complement observations. Supercomputers simulate universes, tracking billions of particles of dark matter and gas, following the growth of galaxies. The stretch of expansion. By comparing models to data, scientists test whether the universe behaves like Einstein's geometry or something stranger. Some simulations explore exotic scenarios, big rip futures, vacuum decays, bounces, or collisions of universes. These are not mere thought experiments. They are numerical laboratories where theories of rupture live or die. Even philosophy finds its place. The holographic principle, the nature of time, the possibility of emergent spacetime, all are tested indirectly. By these tools, the precision of cosmological surveys, the sharpness of black hole imaging, the whispers of gravitational waves, they feed into interpretations that stretch beyond measurement. For while science is empirical, the ultimate question, what happens if space-time tears, remains partly metaphysical. The tools build the scaffolding. Interpretation builds the meaning. Every advance is accompanied by humility. LIGO's detections were a triumph, but they heard only the loudest collisions. The Event Horizon Telescope saw shadows, but not the singularity. Webb glimpses the dawn, but not the birth. Accelerators probe quantum fields, but only at energies far below the Planck scale, where rupture would be decisive. Each tool brushes the edge, never the heart. And yet, with each, humanity steps closer to the moment where speculation becomes knowledge. Perhaps the most haunting realization is that these tools do not merely study space-time, they are woven into it. Every laser beam in an stretches across the same fabric it measures. Every photon caught by a telescope has traveled across the fabric whose fate it questions. The instruments are not separate from reality. They are part of it, fragile eyes built from atoms within the fabric they test. In this sense, the act of measurement is itself a meditation on impermanence. We study the fabric even as we are made of it, even as it may tear beneath us. Future generations may hold instruments unimaginable today, quantum detectors sensitive to Planck-scale foam, spacecraft capable of intercepting cosmic strings or brain collisions, telescopes that see beyond horizons through entangled light. But already, with crude beginnings, we are charting the fragility of reality. Already, we are listening to its tremors, watching its shadows, testing its stability with beams and mirrors. Already, we are preparing to answer the question, what happens if space-time tears? For now, the answer remains beyond reach. Yet the tools are sharpening, the maps expanding, the simulations deepening, and in each experiment, whether a ripple heard, a shadow seen, or a field probed, the universe whispers back, not in full sentences, not yet, but in fragments, clues, warnings. The fabric is not invincible. It is alive, dynamic, trembling, and one day, perhaps through these tools, its rupture will no longer be speculation, but revelation. Would vanish before its rays reached the earth, molecules would unbind, atoms would unravel, and the very constants of nature would shift into unfamiliar values. Physics would end not with fire or ice, but with replacement, our universe rewritten. In an instant, such a vision is terrifying, yet it teaches something profound, that existence itself is contingent, not guaranteed, and yet even annihilation carries meaning. For to know that the stage may collapse is to know that the play matters all the more. Fragility magnifies significance. A diamond shines because it is rare. A life shines because it is temporary. If space-time is not eternal, if even geometry itself may one day unravel, then every act of awareness, every pursuit of understanding, becomes a rebellion against silence. Philosophers have long wrestled with impermanence. Ancient traditions spoke of cycles, cosmic births and deaths, eternal returns. Modern science, through equations and telescopes, finds echoes of the same story. The Big Bang was a rupture. Black holes are ruptures. Expansion itself is a stretching that may end in rip or collapse. The universe, vast beyond comprehension, shares in the same law as flowers, mountains, and civilizations. It begins, it changes, it ends. To contemplate the death of space-time is to accept that the universe is not immune to mortality. But there is another side. Fragility is not only loss, it may also be doorway. When physicists speak of rupture, they sometimes imagine what lies beyond, hidden structures deeper than space-time, substrates from which geometry itself emerges. If space-time is torn, perhaps it does not end reality, but reveals it. Perhaps the tear is not destruction, but transition, the veil lifting to show dimensions we cannot yet conceive. To imagine this is to shift terror into wonder, to glimpse that impermanence may also be creation. The holographic principle, string theory, loop, quantum gravity, in its own way, suggests that space-time is not fundamental. If so, tearing it would not erase reality, but expose what is beneath. Just as tearing the canvas of a painting reveals the wood behind, tearing space-time may uncover the deeper architecture from which universes arise. Perhaps our cosmos is not the whole, but a chapter in a larger story, one whose pages are written in structures beyond geometry. In this reflection, humanity finds its role. We are fragile creatures on a fragile stage, yet uniquely capable of awareness. The cosmos may be vast, and space-time may one day rupture, but in the present moment there exists consciousness, a spark that can contemplate its own impermanence. This act, the act of wondering, is itself extraordinary. For while galaxies drift and black holes collapse, while the fabric trembles, life has arisen that can witness it, speak of it, and ask what it means. If space-time can end, then certainty cannot be our foundation. Instead, meaning must be found in the act of living, in the pursuit of understanding, in the weaving of stories across temporary geometry. Science is not a fortress against death, but a lantern in the dark, illuminating as much as it can before the fabric fades. Each discovery, gravitational waves, black hole shadows, cosmic expansion is not only a step toward knowledge, but a testament that humanity dared to ask the cosmos about its own mortality. And so the reflection becomes personal. To contemplate the tearing of space-time is to contemplate one's own death, one's own finitude. The universe is a mirror, and in its possible rupture we see the echo of our own endings. Yet just as we live meaningfully despite mortality, so too can we find beauty in a cosmos that may not last. Impermanence is not emptiness. It is the condition that gives rise to wonder, urgency, depth. What then does it mean to imagine space-time torn apart? It means to accept that nothing is absolute, not matter, not time, not the universe itself. It means to embrace that existence is precious, precisely because it is fragile. It means to see that the cosmos, for all its grandeur, shares the same destiny as every life it hosts, to arise, to unfold, and to end. But within this ending lies possibility. Perhaps a tear is not silence, but a whisper of something more. Perhaps from the ruins of this geometry another will arise, just as stars are born from the ashes of earlier stars. Perhaps universes emerge from ruptures like seeds from fruit, scattering into infinity. If so, then our cosmos is part of an endless cycle, and its death is not erasure but renewal. As the narration fades, the image returns to the fabric of the cosmos. Galaxies drift apart, redshifting into invisibility. Black holes consume, stars burn out, expansion accelerates. The fabric trembles. It is vast, but not invulnerable. And somewhere, beyond sight, perhaps it already frai. In the end, the question remains open. What happens if we tear spacetime apart? The answers are theories, models, dreams. No human will likely see such an event, yet all live within its possibility. The reflection it offers is timeless. To exist is to stand upon fragile foundations. To live knowing the stage may collapse, and to find meaning anyway. The film closes in silence once more. A vision of the cosmos, stars fading like embers, space-time stretched to its limit. Then, darkness. Not an ending, but an invitation. Wonder what lies beyond the fabric. To imagine what truth may be revealed when the threads of existence finally come undone.